Okay, I'm going to debrief in class exercise 2, and it's actually focusing on energy cycle, the drawing on energy cycle, as well as buoyant energy. And of course, fundamentally, for the past a week or so, we are looking at Hess law. Okay, so yeah, we are given this particular reaction. So we have 1 mole of liquid bromine reacting with 3 moles of gaseous fluorine to give me 2 moles of liquid bromine trifluoride. You are supposed to construct a fully labeled energy cycle. You need to relate the reactants and the product to the gaseous atoms. Okay, the reason why they give you this particular clue is actually really to tell you that you need to make use of buoyant energy data, and you need to convert whatever molecules you have into the gaseous atoms. Okay, and of course you are given all this information, especially the enthalpy change of formation of liquid bromine trifluoride is negative 301, and then enthalpy change of vaporization of liquid bromine and liquid bromine trifluoride. The reason why you are given the enthalpy change of vaporization, of course, it's for a very simple reason, because if you remember your buoyant energy definition, it's actually the amount of energy you need to overcome 1 mole of covalent bonds in the gaseous phase. So therefore, there is a need for you to change all solid or liquid molecules into their respective gaseous molecules. Okay, so with that, I'm just going to copy the equation over. So just bromine liquid plus 3F2 gas, and then I'm going to end up with 2 moles of BrF3. Okay, and of course, this actually defines the enthalpy change of formation of 2 moles of BrF3. So I need to multiply 301 by 2. Okay, so we get the first piece of data here, and then after that, we're just going to complete the cycle. Okay, so I'm going to change to purple, and then I'm going to vaporize liquid bromine, and there's only 1 mole here, so I just need 31, and just going to write Br2 gaseous plus 3F2 gaseous, and then I have 2 equivalent of bromine trifluoride. So in order to vaporize it, I need to multiply 44 by 2. Okay, so I'm going to get 2 BrF3 gaseous. Okay, and then after that, the next thing I'm going to do is to change, or is to break all the possible bonds. Okay, so I have 1 equivalent of Br bonds and 3 equivalent of fluorine bonds. If I break everything, I need to refer to the data booklet, and yes, it's given 158 and 193. So I'm just going to input 193 and 158 times 3, and with that, I'm going to get 2 bromine gaseous plus 6F gaseous. Okay, then I will be able to complete the cycle by determining how many bromine fluorine bond I'm breaking. Okay, so of course, this is kind of related to your chemical bonding, because you kind of like need to know the structure for BrF3. Of course, if you do a quick drawing, you should be able to get something like this. Okay, I'm not we're not going to determine the shape now, but of course, if you want to revise your VSEPR theory for your test, you have 5 electron groups around it, of which 2 are lone pairs of electrons. I'm going to put it here and here, so you're going to end up with a T-shape. Okay, so it's a T-shaped molecules. But most importantly, why do we need to determine this? Because we want to determine how many bromine fluorine bond I'm overcoming. So 1 molecule of BrF3 have 3. I have 2 molecules, so I have 6. Let it be A, so it's 6A. Okay, so with this, I'm just going to complete the equations. So I'm going to write 1 equation, 1 unknown. Okay, so I'm going to from 2 BrF3 gaseous down here. So to do that, because I'm putting my unknown on the left-hand side, I'm going to walk through in an anti-clockwise fashion. Okay, so therefore I'm going to get 6A, which is equals to minus 44 times 2 plus 301 times 2 plus 31, and then plus 193 and plus 158 times 3. Okay, so right now I'm going to punch my my calculator. Okay, and I'm going to end up with 1212. Okay, I'm going to divide this by 6. Okay, and then I'm going to end up with 202 kilojoules per mole. Okay, so of course it has to be a positive number, because remember, bond energy is defined as energy you need to overcome 1 mole of covalent bond in the gaseous phase. You need to take in energy to break a bond. Okay, so bond breaking is always endothermic, bond forming is exo. Okay, so getting a positive number is a must. Okay, so right now I'm going to move on to the second question. Okay, so the second question reads, when briefly exposed to a bright light, a mixture of hydrogen gas and chlorine gas reacts explosively to give HCl gaseous. Use relevant bond energy values in the data booklet to calculate the enthalpy change for this particular reaction. So, well, I mean, it's the same thing. I need my data booklet. So, remember earlier on, what did we do? What we did was we break all the bonds to get the gaseous atoms, right? That's the earlier part. So shall we do the same here? So if we do the same here, I'm going to go to the data booklet, and then H2 is 436. So I'm just going to point downwards to get me 2H gaseous. Okay, that's 436. Okay, and then for Cl2, that's 244. So that's 244 plus 2Cl gaseous, and then when I break 2 equivalent of HCl, it's actually 431. So that's 431 times 2. Okay, so with this, I think you can easily complete this particular cycle, because I need to calculate the enthalpy change of this particular reaction. So this will be a anti-clockwise fashion again. So therefore delta H is equals to 430. Is equals to 436 plus 244 minus 431 times 2, right? And then I'm going to end up with negative 182 kilojoules per mole. Okay, so I hope you can see that it's actually pretty straightforward. I know that again in our notes there's things written along the line that, oh, you know, you can easily calculate enthalpy change in reaction by summing bond broken minus summation of bonds formed, but as you always heard from me in the tutorials and the lectures, I don't really like to go through formulas. Okay, if you understand the fundamentals, you don't really need all these formulas. Okay, then the final thing is where I'm supposed to draw arrows on the energy level diagram and the energy diagram below to show each of the bond breaking and bond making steps you have used in your calculation above. Okay, so, well, I mean, that shouldn't be too difficult. Okay, so again, this is the delta H we are talking about. So I'm going to get 2HCl gaseous. Okay, and I think first of all, because this is a smaller region than this, and if I look above, I will realize that 436 is a bigger number than 244, right? So therefore I'm going to break Cl first. That's 244, but this is artificial. Okay, so this is artificial. If you don't wish to do that, you don't have to do that. Okay, so I'm going to get 2Cl gaseous, and then I'm going to end up with 436 here, and then 2H gaseous plus 2Cl gaseous, and then after that, when you break HCl bonds, so that's 431 times 2. Yeah, so again, from here you can easily calculate delta H in the energy level diagram by going in this direction. So plus 244 plus 436, and then minus 431 times 2. Okay, so I hope you find this this useful, and then yeah, I'll see you in school next.